Okay, so we've talked about what polynomials are, and now we're going to get into multiplying polynomials. In 6.1, we talked adding and subtracting. We had a good, pretty good handle on that. It was all about collecting the like terms that we had. 6.2, we're getting into multiplying, and multiplying is probably the next easiest, and then we'll get into dividing later on. Dividing is a little bit more challenging. Okay, so talking about multiplying polynomials and some things I want you to be thinking about. What are some key things to remember when multiplying polynomials? What are some key things to remember when doing binomial expansion? There's really two parts to what we're doing today. The first is multiplying, the second is binomial expansion. Okay, really quick review here. Quick review, just try those three on your own. You can either think them in your head, write them down if you need to, try them on your own. Right? You may be thinking, oh, 3x squared, x to the third, 3x to the fifth. AB times negative 2AB, because b squared is bb, is negative 2a squared b to the third. Hopefully you are 2 for 2. Third one, give yourself a shot. See if you can come up with it as I write these down. Lots of d squareds there. Negative 18, because 3 times 6, negative 6 is negative 18. C squared, d to the fourth. How did you do? Did you remember that when you multiply two powers, you add the exponents of similar bases? 2 plus 3 is 5. 1 plus 1 is 2. 1 plus 2 is 3, right? Ones. And then ones again here. 1 plus 1 and 2 plus 2. And then obviously you multiply any coefficients that you have as well. Okay, so a quick review. That's going to really help us as we start to talk about how to multiply polynomials. So when we talk about multiplying polynomials, there's really two ways to multiply. You can use the distributive property or you can use a lattice method. Both are good. Both give you the right answer. It's up to you. Okay? You just have to, if you're going to use distributive property, multiply each individual monomial. Okay? So this x squared is going to get distributed to everything in that second polynomial. X squared times x squared is x to the fourth. X squared times 5x is 5x to the third. X squared times negative 2 is negative 2x squared. Then negative 4x. Negative 4x is going to get multiplied with everything in that second polynomial. Negative 4x times x squared is negative 4x to the third. Now notice, I'm trying to organize so that my like terms line up perfectly. Okay, that's the look I'm going for. Negative 4x times 5x is negative 20x squared. And negative 4x times negative 2 is a plus 8. Okay? So I just travel that negative 4x to everything in that second group. It's like the distributive property on steroids, right? Or juicing. Okay? Then, negative 1 times x squared. That's going to go in the x squared column. It's just regular 1x squared. 1 times 5x. That's plus 5x here. By the way, this should say plus 8x. I screwed the pooch right there. My bad. And then 1 times negative 2 is negative 2. Now, the whole reason I organized it the way I did is because now I can collect my like terms. X to the fourth has no like terms, so it's just x to the fourth. 5x to the third minus 4x to the third, that's just plus 1, x to the third. Bring that down right there. Negative 2x squared minus 20x squared, that's negative 22x squared, plus 1x squared back, negative 21x squared. Plus 13x minus 2. That's our product. That's from multiplying those two trinomials together. That's using the distributive property. Now I'm going to go back and I'm going to show you the lattice method doing the same problem. If I were you, I'd write down both. Write down both so at least you've seen both. Now, in lattice, just like you do with numbers, you're going to set up the left side and the top with the different parts of your trinomial. Then, we're going to fill boxes. We're going to fill those two. X squared and 5x, x squared and negative 2. Just like we did here on the left side with the red. So this is going to be x to the fourth X squared times 5x is 5x to the third. X squared times negative 2 is negative 2x squared. That looks really familiar. That's kind of how these are related. Then 4x with x squared to fill that box. 4x, I should time out. Negative 4x with x squared to fill that first box. Negative 4x with 5x to fill the second. Negative 4x and negative 2 to fill the last one. So negative 4x to the third minus 20x squared plus 8x. Looks familiar. And then the last one. The 1 is kind of easy because it's just good old 1. Boring, good old 1. X squared, 5x, and negative 2. So every box in the lattice is filled by looking at what column is it in, what row is it in, and then bringing them together. Then we collect our like terms. And the nice thing about lattice is most of the time, if we do it right, our like terms should line up. Okay? Now, let's collect these real quick. X to the fourth. The next diagonal is plus x to the third. The next diagonal is minus 21x squared. The next diagonal is a 13x, and the final little corner is negative 2. Now, something to keep in mind with lattice is, let's say all of a sudden this is an x to the third. We have to sneak in a 0x squared to make that work. We need to make sure every term, cubic, quadratic, and so on, has a spot to live. Okay? So we need to make sure everything's got a spot. So we would just sneak in another column here, and we'd go from there. Now, we didn't have that here. Everything fit perfectly, but when you're using lattice, please be careful of that. Okay? I want you to try. I want you to try one. Here you go. First one to try is the distributive property. Second one to try is lattice. So give those both a try. I'd love to see you attempt both. That would be awesome in my mind if you could try both of them. Okay? Now remember, when you're setting up that lattice, this is actually going to be a 2-row, 3-column lattice. My x and my negative 2, my x squared, 0x because I need a placeholder, and then a 4. So remember, we got to fill that in with a placeholder. Okay, now that you've seen both of them, I want you to try. Check your work. How'd you do? Now, hopefully, you started to see that in that first one, organizing those like terms vertically took a little spacing, right? We needed a little space to make that totally work. In the lattice, if you snuck that 0x in there, boy, it made everything line up nicely on the diagonal to easily collect our like terms right there. Okay? So, no matter what you did, no matter which one you prefer, I hope you got x to the third minus 2x squared plus 4x minus 8. That is my secret wish, that you got at least that answer doing it one way or the other. Okay? That's how you multiply. I gave you two methods for multiplying. I gave you either the distributive property on steroids, or lattice. Right? Distributive property on steroids or lattice. Whatever one you like, that's what I would like you to use. Okay? Now, I said multiplying. Some key things to remember in multiplying. Go back in your brain, pause for a second, and think about some key things for multiplying. Hopefully you got some great ideas on things you want to remember for multiplying. I'm going to show you right now how binomial expansion works. Basically, binomial expansion is taking a binomial, something with two terms, and raising it to an exponent. Okay? So this x plus y to the third, that literally means x plus y, x plus y, x plus y. And we could just deal with these second two, and with FOIL, it would simplify to this. And then we could go full distributive property on steroids, and basically our final answer would look like x to the third plus 2x squared y plus xy to the second plus x squared y plus 2xy squared plus y to the third. Our final answer would be x to the third plus 3x squared y plus 3xy squared plus y to the third. Okay, obviously I did a lot of things kind of quickly right there, but that's not too terrible. However, it is still a little crazy, and in fact, it gets even crazier for larger exponents. Like oofda, holy cow, it's gonna get nuts. Because then let's say all of a sudden I added another x plus y here, or another x plus, that's too many. That's way too much. So there's fortunately kind of a simplified, streamlined version to help us figure that out a little bit easier. And I'm gonna show you how to expand. Okay, we're gonna look at it with x plus y to the third. How to expand x plus y to any exponent. So this n right here represents that I want to show it to you for any exponent possible. So what if I had x plus y to the 0? Well, that's just 1. X plus y to the 0 is 1. Anything to the 0th power is 1. Okay? Then x plus y to the first, well, that's just x plus y. Now x plus y squared, now you're going to have to kind of just hang on with me. But that should look a little bit familiar. From FOIL, right? First times first, outside times outside, last times last. X plus y to the third, we figured out. Now, this is where I said it was going to get a little crazy. Here's what x plus y to the fourth looks like. Wrote that wrong. See, this is what I mean about it getting crazy. Okay, speaking of crazy, I was feeling ambitious, but I'm not going to show you why I did 6. However, I do want you to notice a couple patterns here. The first thing I want you to notice is I want you just to take a look at what are the coefficients on each of the terms here. Now remember, if there's no coefficient, that means there's a 1 there. Hopefully you recognize something with that. And then the second thing I want you to recognize is look what happens to the exponents. Here I started with x to the third. Well, now I have x squared and y to the first. 2 plus 1 is still 3. Now I have 1, y to the second, my bad, 1 plus 2, and now I'm all the way to 3, so it's like I count down and then go back up. I keep handing off those exponents, okay? There is a pattern here, and that's what I want you to recognize. There is a pattern to the exponents, and there's a pattern to how we do this. And I'm going to show you a better example with some actual numbers and how we can walk through it. Really quickly, though, let's just talk about the pattern to the coefficient. Now, the pattern, oofta, what is that? Get it out. The pattern to the coefficients is this, right? This would be our x plus y. This would be our x squared, xy, y squared. X to the third, x squared y, xy squared. This is called Pascal's triangle. And it sets up every coefficient for us for every one that we look at. Okay, and I'm going to show you how it works on this next one. I will have a copy of this for you. I will get you a copy of Pascal's. Let's take a quick look on how it gets used. Okay, I'm going to walk through this example real quick. I want x plus 7y to the fourth. Now I know I'm going to live in the fourth row of Pascal's triangle. So those are going to be my coefficients. Then I'm going to be counting down and counting back up. So my first one's going to be x to the fifth, and then that 7y is technically raised to the 0. So I'm not even going to worry about the 7y here. Then I'm at 4, x to the fourth, 7y to the first. Remember I said I'm counting down, or I'm counting up, depending on which one you're looking at. Then it's 6, x to the, why does this say 5? That's my bad, I'm sorry. It should say 4 and 3. 4 and 3, there we go, let's try that again. Then I'm at x squared and 7, y squared. Plus 4, x, 7y to the third. Plus 1, 7y to the third. That's it fully expanded. Now we can clean that up. Okay? We could get that totally cleaned up, but we'll talk a little bit more about that in class because I know this is tough. So I just want you to look at this for now and come to class with questions on how to do it.